Good morning, everyone in the central and west coast of the US. Welcome to the EOL seminar series. It is my pleasure to introduce our speaker, Dr. Frank Beyrich, at the Lindenberg Meteorological Observatory in Germany, run by the Deutscher Wetterdienst, which translated in English is the German Meteorological Service. In his early years with a meteorology degree at the Humboldt University in Berlin, Dr. Beyrich spent several years as an aviation forecaster, eventually receiving his PhD at the Free University of Berlin. That was followed by appointments at the Fraunhofer Institute for Atmospheric Environmental Research and the Brandenburg University of Technology in Cottbus, Germany. Currently, Dr. Beyrich is head of the Boundary Layer Processes Group at the Lindenberg Meteorological Observatory. And I would be remiss if I did not mention a few notable awards that Frank received. Frank is the recipient of the Söring Medal from the German Meteorological Society and is this year's recipient of the Outstanding Contribution Award from the European Meteorological Society for his relentless activity as the program moderator for understanding weather and climate processes. At the Lindenberg Observatory, a comprehensive boundary layer measurement program has been maintained since 1998, with continuous operational measurements of state and process variables at the Earth's surface and in the atmospheric boundary layer. Dr. Beyrich will be presenting an overview of the boundary layer field site at GM Falkenberg and the richness of observations taken over past decades. We are using Slido to pose questions, which you can ask at any time during the seminar. The Slido window is located below this presentation screen. Do not be alarmed if you do not see your question pop up, because we archive all questions until the end of the speaker's presentation, where they will be revealed during the Q&A portion of the talk. Dr. Frank Beyrich, we welcome you to NCAR EOL, and the virtual stage is now yours.
Yeah, thank you, Jackie, for this very, very nice introduction. And thanks to the people at EOL for inviting me to give this seminar today to you. Hello to everybody on the other side of the globe. Here it's already dark. Night has started in Germany already. And as Jackie said, I would try to give you an overview on boundary layer and micrometeorological measurements at Lindenberg Observatory, Germany. This, of course, contains contributions from many of my colleagues in my group, former colleagues and actual colleagues in my group, but also from cooperation partners, as you will see in the course of the presentation. Oh God, now it's hanging again. Why that? I will start with an introduction of the site and of the history of the site. Then I will give an overview on the boundary layer measurements we are doing here in Lindenberg. We'll spend some minutes to talk about our main application of our measurement program, namely to provide contributions to NWB model development and validation, basically in DWD. And the last block of my presentation will focus on some field experiments, on process studies and testing of instrumental methods we have performed over the last years here in Lindenberg. To introduce the site a little bit to you, we are in Germany, in the eastern part of Germany, about 65 kilometers to the southeast of Berlin, in a rural landscape, which represents itself as a mixture of farmland, forest areas, and quite a number of small and medium-sized lakes embedded. This landscape has been created by the inland glaciers of the last ice age, 15 to 20,000 years ago. The observatory itself is situated on a small hill surrounded by some patches of forest and agricultural fields. The climate in Lindenberg is a mid-latitude climate at the transition between marine and continental influences. Compared to Boulder, I plotted here the diagram of our site compared to the site where you are. So the annual cycle of temperature is a little bit less pronounced in our place, with the winters still influenced by the presence of the Atlantic Ocean in the west of Germany. And the precipitation, of course, is not forced by any orographic influences here in Lindenberg. So we have annual precipitation of about 580 millimeters, 560 millimeters, which is roughly 1/3 less than you experience in Boulder. And the annual cycle has its maximum in the summer months. Coming to the history of the observatory, it has been founded about 115 years ago in 1905 by Richard Assmann, the famous German meteorologist, the one who invented the so-called Assmann psychrometer, a tool to measure temperature and humidity. Every meteorologist has made attempts to work with that, at least during the education period. Observatory was founded at that time as the so-called Royal Prussian Aeronautical Observatory, which already indicates in the name the aim of the observatory, namely to provide measurements in the upper layers, not close to the surface, in order to provide service data sets for airmen. At about 100 years ago, of course, there were no remote sensing systems available, no radars, no lidars, no sodars to do such type of measurements. And even radio soundings did not exist at that time, because the radio transmission of measured signals was not available at that time. So what people had to do was to bring the instruments up into the atmosphere and to get them immediately back, which they did with the help of partly huge kites and balloons, which were released regularly starting in 1905 from Lindenberg, on the average twice per day. Nowadays, we carry the name of our founder, Richard Assmann Observatory, and we belong, as Jackie already said in the introduction, to the German Meteorological Service. This is was connected with a transformation a little bit of the profile of the observatory in the early 1990s after the unification of the eastern and western parts of Germany, when the profile of the observatory was newly defined and newly shaped. And now we focus, in fact, on 4 different directions of doing measurements in the atmosphere, namely the classical aerological measurements, which we have been doing all the time since the observatory exists. Nowadays, of course, with the help of radio sounds. Lindenberg hosts the GRUAN Lead Center, GCOS Reference Upper Air Network Lead Center. We do a lot of remote sensing with ground-based remote sensing instruments to profile the atmosphere. And we have a focus on boundary layer measurements and on radiation measurements. All these measurements serve in DWD, first, of course, to provide climate observations, long-term observations of a lot of atmospheric parameters, to provide support for NWP model development and applications, to provide data also for satellite data evaluation, and to explore the operational potential of new measurement techniques for application in a national Met service. All these activities we focused together under one big headline, which we named the Lindenberg Column, which we consider as a reference atmosphere or an atmospheric comprehensive data set characterizing the physical structure and processes of the atmosphere from the surface up to the stratosphere. This is illustrated a little bit in this sketch, which I like very much because the height scale here is logarithmic, and so the importance of the boundary layer becomes quite obvious because this covers 2 or 3 magnitudes, while the rest of the troposphere is then just only 1. So dealing with the atmospheric boundary layer, that part of the troposphere directly influenced by the presence of the Earth's surface, means that we have to observe or characterize quite a large number of different physical processes, which is nicely illustrated by the sketch of Mike Eck, a colleague from the United States, who tried to summarize everything happening and at the land surface in interacting with the atmosphere by this scheme, which I will not analyze now in detail. It shall just illustrate the real large number of processes we are dealing with. These processes cover quite a large spectrum of scales, show a high temporal and spatial variability, both in the horizontal and in the vertical, and in particular in the vertical, the gradients, of course, close to the surface are substantial. Representing the surface in numerical weather, the atmospheric boundary layer, sorry, in numerical weather prediction models is of course quite a challenge. It's essential because most of our life and most of our human activities are focused on the boundary layer. But it is a challenge because of the limited vertical resolution of NWP models, even if the state-of-the-art models are able to resolve the boundary layer quite well, it's still just a limited number of model layers in the lower few hundreds meters of the atmosphere. Then we have to deal with the problem of area averaging. Even the finest operational NWP models have a grid size now of, say, about 2 or 3 kilometers, so they can resolve processes of between 6 and 10 kilometers, and everything below has to be parameterized. Or if we think of the underlying land surface, we have to find ways to describe the heterogeneity of the land surface in a proper way. Coming to our boundary layer measurements in Lindenberg, we have a special site equipped for these boundary layer measurements, the Falkenberg boundary layer field site, in German Grenzschichtmessfeld. That's why the abbreviation is GM Falkenberg, with a central facility, a 99-meter high lattice tower, quite tall, with just a side length of 1.1 meter, equipped at several levels with instrumentation for profile measurements and for turbulence measurements, and also for some special recordings of trace gases, of ice load and similar things. We then have a flat field with near surface small towers, with soil measurements, radiation measurements, and of course turbulence measurements over this grassland surface. And we in Falkenberg exploit a number of remote sensing systems, basically a solar system and Doppler lidars. Falkenberg is nicely situated in the broader view here as this L-shaped area in this larger region that is governed by this quite remarkable heterogeneity from a mixture of farmland, of forest patches, and of the lakes in the background to be seen here. At Falkenberg, of course, we have to operate sensors to measure air state variables, to measure soil, radiation, precipitation, turbulence. So this just gives an overview on some of our basic instrumentation we have on the site. Since the forest represents quite a significant extent of the area with regarding to land cover, we have built up a second station in the forest west of Falkenberg. It was not that easy, but finally we managed to find a fairly homogeneous area of forest. It's a pine plantation, and our tower is here in the middle of this patch of forest. Here the tower is not that high as in Falkenberg, so we have increased it up to a height of 30 meters and do profile measurements and the same measurements on the energy budget and on the soil parameters as in Falkenberg on that forest side. And as already mentioned, a third component that significantly contributes to our boundary layer measurement program is the remote sensing measurements with sonar, with LiDAR, with scintillometers at the observatory site in Lindenberg, also with our radar wind profiler and several more remote sensing systems like microwave radiometry and LiDARs. And together with cooperation partners, we also collected quite some experience and quite some data from airborne measurements using either the helipod in the past, turbulence sonde carried by a helicopter, or nowadays using unmanned aerial vehicles. This diagram shows you a little bit the time evolution of our measurement program and the operation times of different components of that program. Falkenberg itself was set into operation in 1998. We then started a little bit later with the direct turbulence measurements close to the surface, about 8 years later with the direct turbulence measurements continuously at the tower. The forest station was operated over a few years at the end of the 1990s and then set into permanent operation by the end of 2002. We have collected quite a lot of experience and data with operating scintillometers, both on the small scale and on the regional scale. This was supplemented, this started with optical instruments and was supplemented by a microwave component in 2015. And from the remote sensing part, we now focus on operation of Doppler lidars, with which we started to measure also about 5 years ago. We then have implemented a comprehensive scheme of doing quality assurance and quality control of our measurements. I have separated this scheme here into 4 blocks. The first one is done only once at the beginning of the measurement program and consists of site selection, characterization, sensor selection, characterization, and the station setup. And then cyclically, we have these other 3 blocks of operation, the instruments, including maintenance, first data checks, then a block involving data quality control, both automatic and also for those data that were flagged as suspicious, then there is often a manual control which follows the automatic one to decide whether there is a problem with the sensor or whether it's probably even a real event occurring in the atmosphere. And finally, we consider it quite important to have a user dialogue. So users that take our data, we ask them to give us feedback, which sometimes even helps to discover issues with the data and may even result in some recalculation or revision if necessary. I will present a few examples from our long-term measurements. This graph is a standard graph you can produce if you have wind measurements at different altitudes. Here in our case along the 2 towers, between 0.5 meter above ground and 98 meters above ground, showing the mean diurnal cycle averaged over 15 years. This is the usual picture that is known to boundary layer meteorologists, that we have near surface features which are represented by low wind speeds at night and higher wind speeds during daytime. And this pattern changes at some decameters above ground, so that at the higher levels, we have the higher wind speeds during nighttime and on average the lower wind speeds during daytime. And in Lindenberg, the level where this change takes place is at roughly 60 meters above ground. If we have long data sets, we can of course also look for the time evolution in the scientific community, and also driven by the interests of the wind energy community. There has been quite some discussion over the last decade or 5 to 7 years on the phenomenon of terrestrial stilling in the mid-latitudes. That's a phenomenon that has been discovered in quite a number of standard wind observation time series in mid-latitudes, that the mean wind speed seems to be decreasing with time. And that's of course something wind energy people start to worry about. And taking all our measurements, we have investigated our data sets for this phenomenon. And you see in this diagram in red, our standard observations in Lindenberg at the observatory site at 10 meter, which indeed also show such a slight decrease. And the same holds for the measurements at our forest tower, the green line below. But all our measurements at the Falkenberg tower do not really show any clear tendency. So they vary a bit from year to year, but there is no significant trend anyhow over these 20 years. And this is supported by measurements a little bit higher up at about 1.5 kilometer as derived from our routine radio soundings and from the wind profiler measurements, showing or indicating that most likely the influence of decrease of wind speed with time on the average at Lindenberg Observatory and at the forest station is related to changes in the vegetation and in the surface characteristics immediately around the site. Looking at the wind, we can also have a look at temperature time series. Here are two examples of an analysis a student made with us just this year, looking for surface inversions. And the left plot shows you the monthly occurrence frequency of surface inversions, which are deep enough to cover our the full depth of our 98 meter tower. So surface inversions of a depth of at least 98 meters over the averaged over 2001 to 2020 with a double peak in the annual cycle. So the frequency of deep surface inversions, I would say, accumulates once in spring in April and again in the late summer, early autumn with a peak in September. The right plot shows you the time series of the intensity from 2001 to 2020 over the 20 years. There seems to be not much changes. If you try to put a regression line through it, you will come up with a very slight increase, but this is not significant at all. And it shows, and then we have some remarkable surface inversion events, in particular over the last years, with inversion intensities up to 12, 13 Kelvin across this layer. A little bit more applied is then to have a look at the soil moisture and precipitation over a longer time scale. Here we have our soil moisture measurements down to 1 meter depth plotted as a depth time diagram over 6 years, showing quite remarkable differences, in particular between 2017, where we had quite some high precipitation, in particular in the early summer, so that the drying, which usually occurs in summer, did not happen at all. And then the very dry summers from 2018 to 2019 and 20, whereas 2018 was in fact the driest. And then we looked at how this dry summer is reflected in the Bowen ratio annual cycle. And the right plot shows you the mean annual cycle of Bowen ratio at noontime from 2003 to 2017 compared, this is the black dots, compared to 2018, which is the red dot. And as you can see, normally we have Bowen ratios on the average between 0.5 and 1, which means that there is always enough moisture available so that the latent heat flux can dominate over the sensible heat flux. But during this dry summer in 2018, we had 4 months in sequence with mean Bowen ratios at noontime above 1, indicating that there was really a shortage of water in the soil. One instrumental aspect at the end of this part on our ABL measurements, we have, as I said already, quite some experience with the long-term operation of scintillometers to derive latent sensible heat fluxes from measurements of the high-frequency fluctuations of a light signal that is propagated over a horizontal path. And this slide is to illustrate a little bit the availability of data from these type of instruments, which shows that they are really quite robust and suited for long-term operations. So the left diagram shows the technical data availability of data of the first type of large aperture scintillometer we had in use over about 16 years. And as you can see, the breaks are really short periods only. And there's in fact only one break that was really related to the instrument. That is this one here in 2004, where the LED from the transmitter became so weak that we had to resend the instrument to implement a new light source. But all the others were things that happened with the infrastructure. And on the right figure, you can see for the short range laser scintillometer installed at Falkenberg, the percentage of good quality sensible heat flux according to the quality checks that are implemented in the system software. And this shows that except of a few periods where we had some data gaps, in general, we can achieve 85 to 90 or even 95% of good quality heat flux data from these measurements. With the third block, I will speak a little bit about contributions of our measurements and data to NWP. This has quite a number of aspects, and I will try to put an eye on a few of them, starting with operational diagnostics and going to case studies and parameterization development. What we are really doing operationally is to create plots of our measurements versus the operational NWP model output, both on a daily basis and also on a monthly basis, as shown on this slide. So here you, just for illustration, this is our global model in DWD for our grid point with the forecast started at the different times versus the observations, the black line, and this is a period from winter this year, when the model gave much too low nighttime temperatures for 2 nights, simply because there were low clouds present in the observations, which were not in the model, and so the model suggested a strong cooling, which was not observed at Falkenberg. Lower plot shows a little bit from our local scale model, Icon D2, which has 2 kilometers of resolution, the time series from summer this year of latent and sensible heat fluxes from the observation versus the model. And one can see that the model has a problem in splitting the available energy. So the sensible heat fluxes are much too high, the latent heat fluxes are a little bit too low. And even if we have to consider that, as many micrometeorologists, also we with our measurements are not able to close the energy budget fully, this would not explain these differences. Right figure shows a mean monthly diurnal cycle for a summer month of TKE at 90 meters, showing that the model is producing a little bit too few TKE during daytime. And the lower plot shows a problem in our model with the soil temperature modeling. Here is a difference plot between the observations and the model, so not 2 time series separately shown as in the other plots. And you see that in the model, simply the diurnal cycle of soil temperature at 5 centimeters much too high when compared to the observations. So we can drive this further, even to go for then long-term measurements and comparisons. So here this is 15 years of comparison of the temperature difference between 100 meter and 2 meter between the measurements and the model. And you see here the scaling is the same. So you already see there is quite some differences. And here is then the difference plot, where you have to note that the 0 is the light orange, so not the green. So 0 is the light orange, and all what is green is showing a problem, which we mainly have with our model in summer, that the model is simply overestimating the nighttime temperatures in summer. The next step we did is to do a kind of cluster analysis. That's the advantage you can do if you have really collected data over many years and decades, so that you can start to stratify your data and still have enough members of each class, even if you go for 10, 20, 30 classes. What we did here is, that was a request of our modelers to look for an evolution of the convective boundary layer with and without cloud formation. And we took these data out of our database by a conditional database request, and then we classified them according to stability, radiation, and wind. Took 3 classes for each of that, which immediately results, of course, then in 27 single classes, and then looked for the observation days that fall into the different classes and grouped them accordingly and made the comparisons. And I only show here one example of clear sky conditions with weak to moderate winds and medium stability for 3 different radiation classes. And this is the cases always that fall into the class, and shown is here the modeled versus the observed curves. The observed are the solid lines and the model is the dashed lines. And what you can see is this for the low radiation class, which mainly corresponds to winter, the model seriously tends to underestimate incoming radiation even under clear sky conditions. And this almost vanishes for high input radiation, so for mainly summer cases, and it's intermediate in the transition periods, which was a hint for our modelers then to look for their aerosol parametrization, because in winter the way the radiation has to go across the atmosphere is much longer than in summer with high elevation angles of the sun, and this brought them to look for their aerosol parametrization. A case study example from a winter case with snow in Falkenberg, which we did analyze because here is a few days the evolution of temperature, of 2 meter temperature, which dropped down to -20 centigrade, quite remarkable, but the model was hardly going below -15. So this is quite a severe error of underestimation, although the cloud observations were not too bad. The cloud modeling compared with the observations was not too bad. So we looked into these data a little bit more in detail to suggest possible reasons for this problem with the model. And there were two issues we found. The one is the temperature in the soil is shown here. The green one is the observation as well. Almost no diurnal cycle, almost no time evolution, which is not very much surprising because we had the snow cover here, but in the model, the soil temperature dropped quite significantly. So that means there was too much heat exchange between the soil and the atmosphere across the snow. And similarly in the atmosphere, the cold nights is this period here, we had measured heat fluxes around 0, but the model consistently brought -30 watts per square meters at night, indicating that there is also too much heat transported downward to the near surface air layers. And in the end, if we have too strong heat exchange with the soil and too strong heat exchange with the air layers above the ground, then of course temperature cannot drop that much, as we did find in the observations. A last example from this NWP work shows how we contributed with our measurements. In this case, it is soil moisture to parametrization studies. When comparing our observations, again, this green curve with the corridor of uncertainty versus the standard model run, we found that the model over several years tended to significantly underestimate soil moisture. And then our modelers did a lot of studies in changing things in the parametrizations, considering bare soil evaporation, modifying the root density distribution, replacing standard values for leaf area index and plant cover from values they had derived from satellite data, and something more. And in the end, they were able with that to reproduce the measurements quite better than before. Yeah, the final part of my presentation will focus on some field experiments we did over the year. I have selected the 3 major field experiments we did during the last 20 years. The first one was LITFAS 2003. This was a field experiment aimed to study the aerial aggregation of surface fluxes over a heterogeneous landscape. And we had put quite a number of measurement systems in our area. Here is the observatory site, Lindenberg. Here is the boundary layer field site, Falkenberg, about 5 kilometers apart from each other. And we have installed all the red points is Eddy Corian's flux stations over different types of surface, both grassland, forest, even lakes, and different types of farmland. We have operated 3 long-range scintillometer paths during that experiment. And we did some measurements with this helicopter-borne turbulence sonde I was mentioning already earlier, and even some trial with combining LiDAR and radar RAS measurements to possibly derive fluxes, which was at that time with this type of instrumentation not really successful. To illustrate the results with one example, this is one of the nicer days with dominating clear sky conditions in May 2003, showing the diurnal cycle of the sensible heat flux on the left and the latent heat flux on the right over the different types of surface. And as you can see, there's quite a remarkable spread in the sensible heat flux, with the forest dominating everything, and then the farmland even differs by a factor of 3 to 4 between the different types of farmland during daytime, and the lakes even had a negative heat flux at that time, because this was in May and the water was still relatively cool when compared to the environment, so that even at daytime there was no upward sensible heat flux. The latent heat flux does not show that drastic differences, but they are still remarkable for the different types of farmland between, say, 120, 150 up to 300. So that's a factor of 2 to 3. The forest, of course, is now on the lower edge, because the pine forest spends most of the available energy into the sensible heat flux. And the water, although it's an open water surface, still has the lowest values of latent heat flux, simply because the stratification was stable, and this, of course, prevents then effective evaporation. And then we tried to bring this together. We created a composite for the farmland, and we smoothed a little bit the forest measurements to have a, so to say, one curve for farmland and one for forest. And then we compared, this is the solid lines in this plot, and then we compared this with the scintillometer measurements over farmland and over forest, and with the derivations from the helipod, which is the dots here. And as you can see, we were able to nicely match these 3 different strategies of determining area averaged fluxes. And this was one of the first trials that gave us quite some confidence into the scintillometer measurements, that because they are easily to run operationally, as I have illustrated, and so they really form an alternative to put a dozen or whatever surface flux stations into an area like that. The second field experiment was LITFAS 2009. Here we tried to focus even more on the scintillometer measurements, and what we wanted to do is to verify the original parameter derived from these scintillometer measurements, namely the area averaged structure parameter of temperature, by flying with an UAV along the scintillometer path, and even supporting this by putting surface stations with laser scintillometers on the 4 major fields along that path. But in the end, we were not really completely successful with that try, as it is illustrated in this slide. First, we saw that there is quite some variability of the temperature structure parameter along the path, even at a height of 40, 50 meters above ground, as derived here from the aircraft observations. But then deriving CT square diurnal cycle for several days from these measurements, we found that we were not really, I mean, we were able to reproduce the diurnal behavior in the same way from scintillometer and aircraft measurements. So you have the high values during daytime, and then the decrease over 2 orders of magnitudes towards the morning and evening transition periods. But in the end, our aircraft measurements were always about a factor of 2 too high. So this has not been solved at that time. We applied for funding to repeat this experiment with better sensors on the aircraft, and also extending it to humidity. But so far we were not successful with getting funding for that. But it's still a thing I have in mind to do once if we will be successful. And finally, I will spend a few words on the festival experiment. That was a field experiment on sub-mesoscale spatial temporal variability, which we did just this year. As a quite challenging enterprise, taking into account all the limiting boundary conditions coming from Corona. This festival was initiated by the Hans Ertl Center for Weather Research, a joint program of DWD and 6 German universities and 2 Max Planck institutes. to do basic research relevant for weather forecasting and climate monitoring, and also to strengthen the meteorological education at universities at fields that are relevant for DWD. And with this experiment, we focused on sub-mesoscale variability for the following rationale: with NWP models, even with the finest, with a grid spacing of 2 kilometers, we are not able to resolve things that happen in this area. With large eddy simulations, we are probably able to simulate them, but we still have to rely on parametrizations, which need to be verified. And if you want to have data in this scale, existing standard observing networks are simply too coarse to provide validation data sets for models. And so we designed a special experiment, and then we decided to focus on 3 types of sub-mesoscale variability, namely on convective structures in the convective boundary layer, on cold pools associated with showers and thunderstorms, and on wind gusts. And for that, what we did is to build up, that was mainly an initiative of the University of Hamburg, a very dense network of about 100 surface stations around Lindenberg at several circles with increasing radius. The distance got a little bit larger between the stations to measure at least temperature and pressure to detect these cold pools. But this is all the blue stations. All the red were fully equipped automatic weather stations that also provided precipitation, humidity, wind information. And as a second component, University of Berlin, they implemented a citizen network with very simple self-built stations where the data were collected via LoRaWAN. And this is, of course, a completely different thing to do such an approach with citizens. First, they are not experts, so each of them puts the station at the place where it thinks it's reasonable, although we gave some guidance. Maintenance is completely different. And then, of course, stations are not regularly distributed, but clustered according to where the people live, and also considering the range to reach the LoRa antenna and the gateway. And of course, the availability of measurements from these stations in time is not continuous. So that this is just a snapshot illustrating green is data active. Yellow is those who have stations active. Green, yellow is those who provided data within the last 1 or 2 hours, and red are those who did not provide data for more than 2 hours. And then we implemented further 3 super sites in this area. Lindenberg, Falkenberg we have, and we acquired a 3rd one temporarily. These super sites roughly formed an equilateral triangle with about 6 kilometers of side length. And these super sites were equipped with quite a number of remote sensing systems, Doppler lidars in particular, and microwave radiometer profilers. And we did in Falkenberg UAVs measurements and soundings, and we also did additional radio soundings. And these Doppler lidars were operated in different scanning configurations with the purpose to do different types of measurements at these 3 sites. In the end, we put 8 of them together to make some intercomparison exercise. So this is a nice agglomeration of sheep-like Doppler lidars here at Falkenberg. I will show you one example of the measurements. I mean, the experiment just happened a few months ago, so data analysis is still ongoing. As I said, one focus was these cold pools. So the cold air outflow from thunderstorms and showers. Showing here one example from the 29th of June. We called that cold pool Yogi because that was the day when Germany at the soccer Euro lost the match versus England, and that was the last match of our federal coach, Jogi Löw. After that, he had to retire then from this post. And what you see here is first the evolution a little bit of these thunderstorm cells, which came from the southeast. First, it was an agglomeration focused basically northeast of where we are. And then it moved and also developed new cells towards west, northwest. which could be better resolved than with the high resolution X-band radar situated at Falkenberg. And the nice thing was that at our supersite Falkenberg, which is roughly here, there was no precipitation at all. So the whole cell passed north by Falkenberg, but nevertheless, although there was no precipitation signal, we had a very sharp drop of temperature by about 5 Kelvin, and we had a clear signal in wind speed with highest 10-minute average of about 13 to 14 meters per second during that cold pool. The upper diagram here now shows the temperature curve from a second site, from the second supersite Burkholz. That one was hit by the thunderstorm, so it got precipitation. And here, of course, then the temperature signal is even much more pronounced. The drop is within 10 minutes by about 10 Kelvin. And the lower plot shows a map of the measurements from these 100 stations distributed in the area, temperature color coded, with a time separation of about 20 minutes between these three pictures. And you can clearly see in the first picture here, there is still the warm air dominating over most of the area, except of the outer eastern part. Then the thunderstorm and the cold air moved towards northwest, so the warm air remained just in the western and southwestern part. And at the end, there was just a few warm spots, but colder than before in the southwestern part. And the nice thing also to see is these arrows. They show the near surface wind from this automatic weather station, and they clearly show this pattern of divergence originating from this outflow of cold air with winds towards southeasterly winds here directed towards northwest, and here easterly winds, and here it's northeasterly winds. So nicely to be seen here, this cold air outflow from the thunderstorm cell. Our drone people from DLR, they even tried with this type of racing drones to catch the cold pool. So here are wind measurements they derived from this drone operation compared to the tower measurements at very, very high resolution. And you see they managed to get the onset, but then they had to go down because several of their drones were just pressed towards the surface, so they could not hold in the air longer due to the gustiness of the flow at that moment. And then we also made a trial to derive wind gusts from the Doppler lidar, which is of course quite a challenge, because with the Doppler lidar you are not able to measure the three components of the wind vector at one instant. So it always takes some time before you have three independent wind measurements to derive the wind vector from. And we went to the edge of what is possible with these type of wind lidars and operated them in a special mode, continuous scanning, doing these scans, and one cycle within 3.4 seconds, so that we are nearly at the rate where we are able to mainly to resolve wind gusts. And the upper plot shows for this Yogi case on the 29th of June, 10-minute values of mean wind speed and of the wind gusts from the tower measurements. That's always the blue curves. And from the LiDAR, that's the red curve for the mean wind, and that's the dots for the highest instantaneous wind value we were able to derive. And in the end, it looks quite promising, as that we might be able to catch gustiness of the wind by this special LiDAR operation mode. So this brings me to the end of my presentation. I have just a few, I mean, this was an overview presentation, so there is not really a deep scientific conclusion that I can give now. I would like to make a few remarks. We perform in Lindenberg a comprehensive operational micromet and boundary layer measurement program. We have now data sets for more than 20 years, which cover a wide spectrum of weather conditions, which makes this data set also suited really to look into different types of weather situations, but even have available kind of ensemble data sets for this. We have experience with field experiments, and we have also the infrastructure to run these field experiments, and we have done a lot to try to support both the research community and also the NWP model development in DWD with the help of our site, of our measurements, of our data. yeah, thank you for your interest and attention, and I am curious to see your questions.
I'm curious to see the questions too, Frank. So, thank you very much for the comprehensive overview of boundary layer and turbulence measurements at the Lindenberg Observatory. There's certainly an overlap in the measurement system there and at EOLs, and I'm certain that the audience is appreciative of learning how our European counterpart runs this program and all of the exciting campaigns that Lindenberg has participated in. So we definitely have time for questions. Again, please use the Slido interface below the presentation screen to ask your question. Because this is a virtual meeting, we're hoping that the audience members are judiciously crafting and typing some questions on Slido. But in the meantime, I do have a question to ask. It's more of an instrumental question, but in the winter seasons, how do you handle the ice and the snow accumulation in your sensors? What are your de-icing or moisture removal procedures?
Yeah, I mean, to be honest, icing and snow is not that a big problem at our site. So we seldom experience snow and ice in an amount like you may be familiar with in Boulder. So in the last decade, there were a lot of winters almost without any snow. This is not that a severe problem. We have a few of the sensors that are heated, which helps to keep away at least limited amounts of snow and of ice. We have a few that are operationally heated. We have a few that we can heat, but we do not do it regularly, but only with putting it on manually to de-ice the sensors. And yeah, in some cases, of course, where we can do nothing, we lose some measurements. That can happen. Yeah, but as I said, it's not that a dramatic problem at our side.
Are your data publicly available?
Not yet fully public. I mean, we are working on that in DWD to put all our data sets on an open data server, which will be implemented, I think, within the next year, I would say. At the moment, we can send data upon request. So we serve, if people send us an email or whatever in request, they can get data they want to have from us. So the data policy of DWD is basically open in the meantime. So that is all these data that have been acquired have to be made publicly available, at least upon request. That's what we are doing at the moment. But DWD is gradually increasing the number of those data that they make really available on an open data server. But of course, they started with the operational network data, which are of much more interest also for assimilation studies of other wet service, met service, and all these things.
Okay. Looking forward to seeing your data. It'd be nice to do some comparisons, the way that you've done some comparisons with some data in other places as well. We've got some questions trickling in. I'm going to highlight the first question, which is from Steve Onkley, who runs the boundary layer kind of measurements here at EOL. And Steve asks, good to see you, Frank. We hope we can collaborate more. I'm just curious, given the importance of soil moisture, how and at what frequency you calibrate your sensors.
Yeah, this is of course a good question and a tricky question for all sensors that are buried into the soil, because you do not want really to take them out for repeating calibrations. So what we do standard, what we use as a standard is Trime picosondes from IMCO, and they provide a calibration check procedure that we implement before we bury the sondes into the soil once to check their calibration by putting the sondes into a basket filled with water and some pearls, so which represent, if you mix these pearls with a well-defined amount of water, then that should correspond to a certain degree of soil moisture. That we did with all the sondes before we put them in the soil. When having the sondes once in the soil, we do not do regular calibrations anymore before we remove them. But what we do is, I mean, the standard TRIME picosondes are buried at defined levels, depth levels, horizontal into the soil. And what we additionally do is we operate TRIME sondes that can be brought down in a tube vertically, so that we have still always control measurements. We do from time to time gravimetric measurements, but in Falkenberg to a limited extent, because of course we do not want to make too many holes into our place, which shall be stably working over decades. But we did gravimetric measurements from time to time, and we have now, in cooperation with the Environmental Research Center Leipzig, also installed CRNS probe in Falkenberg. So we have in the end different ways to get soil moisture information, which we can try to bring together. And yeah, that's what we do with the soil moisture.
Thank you for that question, Steve. We have a question from Holger Vermel. Thanks, Frank, for this nice talk. You nicely demonstrated the strength of continuous boundary layer measurements and dense networks. You mentioned some of the challenges of the UAV. In your opinion, what role can UAV play in boundary layer observations that cannot be done with existing instruments?
Yeah, that's a very nice question. And of course, we are thinking a lot of UAVs. So far, we have only operated UAV together with cooperation partners. So it was mainly then the partners from university or from DLR who were with us in flying UAVs, both fixed wing UAV and these multicopter drones. But I still think that there is quite a potential. So we currently are really thinking of trying to set up a test program for more or less operational application of at least a copter drone to provide regular profiles of temperature and humidity and possibly wind in the lowest, say, 1 kilometer. I mean, of course, drone operation has always the issue that you need a flight allowance, which is not that easy in Central Europe. And it's also not that easy at our side, because we are not immediately in, but still close to the flight sector of the Berlin airport. This is certainly limits a little bit the operation of drones with respect to height, but there is a clear need from our NWP people that they would like to have more regular profile measurements from inside the boundary layer. And of course, we have the dense surface observation networks. We have a few radio sounding stations in Germany, about a dozen. We have 4 radar wind profilers. But if we think of the horizontal variability of temperature and humidity and also wind fields in the boundary layer, this is of course for a country like Germany not really a very good coverage with profile measurements. And we also have in Lindenberg running a project in the WD to try to set up a network, possibly of remote sensing systems for providing regular profile measurements inside the boundary layer. Doppler lidars, dial and microwave radiometer profilers. But of course, all of these remote sensing systems also have their limitations. And then it's also rapidly going into a cost issue, because I mean, with remote sensing, you almost need a new instrument for each parameter. So the big advantage I see of in situ instrumentation is that you can put different sensors into one carrier, like our tower or like a drone. And of course, the UAV can extend our tower much beyond the 99 meter we have. So we could probably aim for getting with just one type of well-equipped instrumental drone, regular profiles up to 1,000 meter. And we are currently really thinking of and planning a kind of demonstration project or test phase for these operational capabilities of these drones. I mean, of course, it's always a question then, taking a whole year with all the variability of weather across the year, when can you really operate it? And how many situations will it not be possible due to too high wind or due to fog or whatever. But it's really drones are really, and UAV are really something we are thinking of to spend more effort on exploring their capabilities for more operational use.
Great question, great response. So it seems that in the meantime, the value of in situ observations remains. And we have a question from Scott Spuler, who says, in your opinion, what observational gaps should be addressed to provide the most scientific benefit? In other words, what measurements would you like to have that you don't? So in an ideal world, Frank.
That's difficult. I mean, a little bit. It goes into the direction I mentioned earlier. We really would love to start with UAV, which we do not have so far. Of course, we know that we have already quite a zoo of instruments in operation, and this is also quite challenging to keep all these instruments running and to make something out of the data. And I mentioned this what we call pilot station remote sensing project, where we explore different state-of-the-art remote sensing systems for their usability in NWP. And this project already comprises microwave profilers, Doppler LiDAR, Dial, and Raman LiDAR, and cloud radar. So this is already quite another series of instruments. And with that, we could already do quite something, I think.
It's a lot of instruments. Thanks, Scott, for that question. We have one, I think, final question from Ned Patton at MQ. He says, hi, Frank, thanks, enjoyed your talk. I'm curious, in your Lightfast 2003 analysis to produce composite fluxes, can you comment on how or if you accounted for canopy-induced roughness sublayer influences on Monin-Obuchov similarity theory when inducing fluxes from your scintillometer measurements?
Yeah, to be honest, I have to say that we did not account for that. So we simply, scintillometer data analysis assumes Monin-Obuchov similarity. That's true, which is of course questionable. It might be questioned over a heterogeneous landscape, but then we still rely on that we have a kind of blending height where probably the influences are not of the single patches, if they differ not too much in their surface characteristics, are not seen too much, and this is a little bit the assumption that is behind, and therefore we also separated the scintillometer over the forest from that over the farmland, that we did not have to treat with both in one. In fact, we took the vegetated surface as a big leaf for this type of analysis.
Thanks, Ned. Interesting question. So looks like we are past the seminar hour. If you are interested in Dr. Frank Beyrich's presentation and have further questions, please reach out to him via his email, which is provided on the seminar flyer. On behalf of NCAR and EOL, I would like to thank Dr. Beyrich on his excellent presentation on long-term observations at the Lindenberg Observatory. Thank you, everyone, and have a great day.
Yeah, thanks for the chance to be here. And of course, I'm willing to answer whatever you are interested in by email.